So luckily, Vigeli's talked before me, so I can actually skip many of my slides. That will be nice. But this is work from user behavior modeling with large-scale graph analysis. Let's see if this was. And so first, I want to thank, of course, KDD, awesome funding support, and really the awesome collaborators for all of the work, some of which is included here. I'm really going to touch on only a few pieces of the work, unfortunately, but really a lot of it came from discussions with these people across other papers as well. So we're going to consider interactions, which we can think of as sort of networks, usually heterogeneous networks, where we have different types of nodes. So we can say von Neumann, let's say, eats at McDonald's. And we have, it turns out, all of these scientists, Erdos and Grace Hopper and Alan Turing and Marie Curie, all are coffee addicts at Starbucks. Let's say Turing likes Ben and Jerry's. And this provides this network of interactions between users, or scientists in this case, and fast food. And we can look at sort of many networks online as falling in this category of users of some type interacting with different types of other items in the world. So we can say, we can observe what people buy on Amazon, what they watch on Netflix, listen to on Spotify, code on GitHub, a whole host of things. And social networks are sort of a subset of that, where people interact with other people or things they like. And I'll mostly focus on this user behavior, but this is really true across many other applications as well. We have education data. We look at, let's say, what people learn from textbooks or online resources. Healthcare, what symptoms people report, or what sort of medication they're on. And there's applications that are related in security, in distributed systems. And really all of these different sort of domains and the networks they provide for me as a computer scientist, interesting application challenges, problems that these domains need to solve, and we can use these networks as ways to solve those problems. And the tool that I use to solve those problems is modeling. Right? We consider, how can I understand and design predictive and descriptive models of these networks that can solve these application challenges. As I mentioned, we're going to mostly focus on user behavior modeling. So we say these people go and like musicians like Adele, newspapers like the Washington Post, or organizations like the ACM, or the Queen, let's say. And we can ask questions like, who do we think would like what? Do we think Erdos would like the Washington Post based on everyone else's behavior? We could say we can observe lots of context of these interactions. Right? These aren't just some interaction. They have often lots of metadata that goes with them. So the rating, say von Neumann gave Adele a 5-star rating. He might give a comment like, the Washington Post is insightful. We often know the time the interaction took place, right? So we could say the green time here corresponds to one day, and the red edge corresponds to some other day in this month. We know things about the nodes, about the users themselves. So we know, let's say, that both Erdos and von Neumann are from Hungary originally. And we can try to use all of this context to really give us some more understanding of what the model's predicting and why it's predicting this. We could say, why do we think Erdos would like the Washington Post? Can we provide some context with using the context at hand? And this is really one of the core thesis statements that I'll try to sort of touch upon, was how do we make use of this metadata in these networks? The next thing is, how do we build up these frameworks for understanding these huge, large-scale systems, right? Like the data we have for these graphs are often on the orders of millions, hundreds of millions, even billions of nodes, and many billions of edges. And it's meant to really build scalable platforms for learning these models. These are complex models, and therefore learning them at scale is difficult. So I've actually built up these frameworks and these tools for this. And so one thing we try to do here is bridge both the modeling techniques with the underlying systems. How do you design models that can scale, and systems that can scale for those models? And the last thing is, we want to ask questions both of what's normal, who will like what and why, but also what is surprising and how so. And really, we want to try to bridge these two. They use similar style modeling techniques, but they're often framed as very different problems. In reality, in my opinion, these are two sides of the same coin. And we want to sort of I'll try to show how the same techniques can be applied in both cases. So I'm going to go through sort of all three of these different areas and give like one chapter from each area. But there's a lot more work in the paper to talk about sort of how these pieces fit together. And I'll start with first, how is fraud created? Fraud is a certain type of abnormal behavior that I studied. So as probably is even more well known now than when I graduated, you can go online and buy lots of fraudulent behavior. You can buy Twitter followers, Facebook page likes, Reddit upvotes by the thousands, and as we've seen, this become quite the hot button issue where it really just erodes trust in these services, in conversations on these services, and sort of is just a real problem for both the user and the product. So we can say, let's say Dr. Evil goes and buys a bunch of followers and gets these edges in this graph. We see Darth Vader goes and buys a bunch of followers and he gets a bunch of edges in the graph. Now, one thing that's sort of commonly known in the fraud detection community, really pioneered by earlier students in Christos's lab, was that fraud creates dense bipartite cliques, these really dense subgraphs. But if you look at just the graph structure itself, we say, well, how can we actually distinguish an honest community of computer scientists interested in IEEE and ACM from some dense clique of fraudsters that were all purchased together? We know that one is really fraudulent and one is an honest community. So what does it actually mean to distinguish them? How do we distinguish them? And the technique we use, the tool, is to look at the context. It turns out certain contextual features are really, really indicative of fraud. And so this goes back to modeling how fraud is actually created, what makes it distinctive. So if you actually go online and search to say, I want to buy some followers, I search on eBay, we say we can get 3,000 Twitter followers for 18 pounds, or euros, whichever that is, as an American. We notice a few things, though. It also says they're verified accounts. That's pretty impressive. And they'll be delivered in 24 hours. That's kind of weird. Right? So if you actually look at the graph structure, you'll see, oh, look, all of the accounts liked Dr. Evil at this yellowish red time. And all of the accounts liked Darth Vader at this greenish blue time. And that's really not how most people work, right? Like, I mean, maybe some people go home from this conference excited and will follow KDD, but chances are they won't go and then in 2 weeks all do the same thing again and again and again. And so this is pretty unusual. And so we call this lockstep behavior. It's the same users performing the same actions at around the same time, repeatedly. So if you put this in matrix form, we can say I have this user by pages matrix in the case of Facebook. We say von Neumann likes Adele at the green time, so let's say the 20th day of the year. And we can fill in each node here that has an edge with the color that edge was created, the timing. Now the thing is, if you rearrange the rows and columns, you'll find while there's, let's say, an honest community in the top right there, there's no sort of pattern to who likes what at what time. There are these interesting suspicious lockstep behavior where you see all of the users did the same action at the same time repeatedly. And this is particularly suspicious, and we'll show that in experimentally in a few slides. The question that we sort of spend a lot of time in the paper describing is how do we actually do that rearrangement? That's the algorithmic challenge. I'll give one view. I'm not going to really go through the algorithm in too much detail here, but I'll give sort of one high-level understanding of how the algorithm works. We think of it as a clustering problem in this sort of item time space. So in one dimension, you have the time of liking Dr. Evil. You see there's this time series plot, and there's a spike around, let's say, December 16th. Now, if you look at now the two-dimensional plot of the users who liked both Dr. Evil and Darth Vader, we find each dot is a user, and there's a density around that same date. But it turns out there's a group of users who are also dense around January 17th. And that's sort of interesting, that you have this group that's sort of dense in both time dimensions. And you can keep adding dimensions like Mr. Smithers from Simpsons, and while the rest of the space gets increasingly sparse, these users don't. They stay dense. And this becomes increasingly uncommon, therefore. So we can use many different cubes to find many different attacks on this in this graph. And so the formulation we look for there is, given this user by page graph with edges creation times, we say a cube must lie in at least m dimensions. and it has some width 2 delta t. We want to find where to place the cube, in what subset of m dimensions out of the maybe billion or however many, I don't even remember at this point, how many pages are on Facebook or Twitter. And we want to place the center of the cube. At what time in each dimension, on each page, was there an attack? We want to do this, placing this cube, to maximize the number of users that fall within it. Right? If we find we can place a cube with lots of users, that means they're the sort of suspiciously correlated group. So we offered this copy catch algorithm. This was done on Hadoop in this distributed manner. It was tested on Facebook's page-like graph with over 10 billion likes, around 300 gigabytes of data. We tested its scalability. We see it scales linearly in the number of edges of the graph. We tested, here we say seeds. We start each cube at some random place in this graph, in this high-dimensional space. So we can have many cubes, many attacks being searched for in parallel. And we find as we add more seeds, it again scales linearly. Sort of more interestingly, possibly, is sort of how the model searches. Does it search effectively? So we find that after just a few iterations of this sort of local search algorithm, the model starts to converge. The y-axis here is something about the number of likes that we're catching. It has to be sort of censored because it's Facebook private information. But we see it converges in just a few iterations. But it's sort of easy to converge by just staying still. Like, that doesn't mean you did anything. You just said, I'm not going to move at all. So the question really is, if I run the model or the algorithm again and again and again with different random starting points, do I keep finding new things, or do I always seem to go back to the same? Do I find these, right? And we find is after a handful of runs of the algorithm with random seeds each time, we sort of start to saturate the space. It means we're searching this huge, large graph and effectively finding these densest regions with just a few runs. This was deployed at Facebook. This was now from 5 years ago. There seemed to be some decrease in fraudulent activity. We did a bunch of analysis to understand, were we actually catching fraudsters, and what were the fraudsters? So we analyzed clusters of users that this found, right? Because any individual like you can't label. Like, I can't go and ask this user, did you really mean to like this page? But we can look at this cluster and say, does this seem legitimate? We found that all of the clusters that were discovered by this algorithm were in fact fraudulent. And the interesting thing is most of them were real people. I think we had this hypothesis going in. These were some script that someone ran over a bunch of fake accounts. But in fact, most of them were people that were compromised, often through some malware or browser extension that was sort of ruining their experience. And they didn't know how to uninstall, in fact. So this is one piece of work. This is looking at detecting fraud in graphs when we had this temporal information. We did also some work on static graphs, some work when we have more attributes like IP addresses that are also extremely valuable context for sort of distinguishing normal from abnormal behavior. And sort of it built up to sort of helping Facebook. They sort of developed it there further for Instagram. A version of this was done for YouTube and Flipkart, sort of different extensions. But I want to sort of quickly move on to now the other flip side of this coin, normal behavior. So Vageli sort of has outlined a lot of the sort of modeling structures, but I'll sort of go through some of the background to make sure we're on the same page. We can say, can we predict what the user will do? Do we think Erdos would like the Washington Post? I'd say that this problem became pretty famous due to the Netflix prize around, I think, over 10 years ago now, where they said they'll offer $1 million for a 10% improvement in accuracy for their recommendation system. So, of course, the goal is to predict these edges accurately. But the other goal is to explain why. It turns out even Netflix at the time, they said they wanted a simple interpretable model. The model they got was sort of this crazy ensemble of a bunch of different models that were kind of confusing. And so we want a model that's high quality, but we can understand, according to sort of the Occam's razor view of understanding models. We'll think about this as a matrix completion problem where we have ratings on the edges. So we know von Neumann actually gave maybe a 1-star review to Adele, but a 5-star to the Washington Post. And we can look at this in a matrix form where we say we have Erdos and von Neumann. They both like the ACM. They both don't like Frozen. Von Neumann likes the Washington Post. And so they seem pretty similar. If I had to guess, Erdos would also like the Washington Post. This is sort of the underlying intuition behind most of collaborative filtering. And so the problem definition is, given this super sparse ratings matrix where I've for most users, don't know what they feel about most items, can I design a model, a simple model with a small number of parameters, theta, that can predict the missing values? Therefore, we want it to be low error, right? The real data and the model to have sort of very similar scores, and the number of parameters theta to be much smaller than the number of ratings. I'm going to go through this pretty quickly since this is similar to the intuition Vegeli's game on tensor factorization. We can think about, let's say, the movie Frozen being embedded in some low-dimensional space. So we say it's a little bit romantic, it's a little bit science fiction-y. It's not as much of a comedy, but it's definitely for kids and definitely a musical. And it turns out, let's say, Erdos loves romantic movies and science fiction, hates kids' movies and musicals for whatever reason. And we take the dot product of these preferences, and we find that Erdos has a predicted rating of a 0.61. You can do this. Of course, we don't actually observe these attributes, right? These are all latent concepts. But you can sort of, using the techniques Vegeli's mentioned, try to figure out, okay, this is actually the science fiction column or genre, and this is the musical column or genre. And we can do this for every user and for every movie. So you have this per user and per movie embedding, we get the dot product, get the prediction, which corresponds to this UV transpose for the prediction task. Now, if you do this with squared error, you're really predicting a Gaussian. So one thing in our work we looked at was, well, that's a pretty strong assumption, actually, and often wrong. So if you look at, for example, CDs on Amazon, they're quite bimodal. Either they work or they don't. You don't have a strong opinion beyond that. And so this is a whole chapter that I'm just going to skip over entirely, but I think there's an interesting question about what's the right way to train these, and we offer one way there. But the question here is, again, simplicity of the model. We can think of this model here, this factorization. The model sizes the blue, dark blue, and the red regions. If there's n users and m movies, r factors and genres, 32 bits per preference, this corresponds to an n plus m times r times 32 bits size model. And this really covers much of the work in collaborative filtering. SVD, SVD++, more fancy things like Lorma or factorization machines really all fall in this category of scaling in this way. On the other extreme is co-clustering, where we say, I'm going to partition the movies, let's say, by their rating, and let's say users by their age. And I say maybe on average, young kids like PG movies a little bit more than average, and they are a little less than average. You know, these very coarse model. Now, of course, these are, again, latent concepts. We don't actually split on these. We can learn these clusters. But the model size is kind of small. We have n user and m movies, kn user groups, and km movie groups, 32 bits per preference. Those 6 values are only k squared, in this case 6 times 32 bits, so tiny. And then we have n log k plus m log k to assign the users and movies to groups. Now, the problem is this is a terrible model, right? You don't want to recommend every kid just every PG movie. That's not very useful. So we can say, let's maybe split up the movies by genre, cross-product with the rating, and maybe people by gender, and maybe also by the year, the decade it was produced, and people by their party affiliation, right? We can keep doing this, but you quickly end up having more combinations than you actually have columns. You'll overfit your training data. You'll just do terribly. If you have 20 binary attributes, you end up with a 4 terabyte model quickly. So the reason being, if you have S types of attributes, it grows exponentially. How can we get the benefits of these discrete models without this exploding cost? And so we offered was this concept called additive co-clustering that I'm going to go through extremely quickly due to time, where we say, let's not do this exponential blow-up. Let's instead think of it additively. We can say we have this relationship between age and rating. We can sort of reshuffle this. It's still a co-clustering, just reshuffled rows and columns. We can, let's say, maybe add this with the relationship between gender and genre. Again, these are latent concepts, not things we actually observe, but we can have these 2 co-clusterings that are simple and capture some rough correlations. But when we take the sum of these rough correlations, it produces actually a much more complex model. And so this is this key insight. Let's consider preferences as sums of discrete attributes. Latent discrete attributes, but discrete nonetheless. When you do this, the model size is a little bit more manageable. If we have S co-clusterings, the same N and M users and movies, K by K partitioning, and 32 bits for each of those block values, this grows linearly in S rather than exponentially. That means if you had the same size data as before, 20 binary attributes with a Netflix-sized data set. It's less than 1.3 megabytes rather than the 4 terabyte model that you would have had otherwise. And so the nice part is it takes this happy medium between sort of soft attribution in factorization models and hard attribution in co-clustering with additive from factorization rather than all combinations in co-clustering. We designed this both as a frequentist and Bayesian model. Pretty much for the Bayesian side, you can think of it as there's a clustering part, there's this sort of Gaussian assumption over the block values, and you can do this conditioning to sum up these different block values. And we provide a sampling-based learning algorithm you can look up in the paper. But the important question is, does it work, obviously? We looked at this on Netflix. Lorem at the time had the best published result, and we found that we were a quarter of the size with pretty much the same exact accuracy. I think kind of interestingly, we tried it also just on graph construction, like matrix completion generally. SVD obviously gets the sort of provably optimal factorization per rank that you're doing. We find per bit of model learned, you actually get better accuracy. So you're getting more essentially bang for your bit, which is a nice property. So this is one piece of work. I mentioned that we had this sort of bimodal shapes, looking at sort of combining normal and abnormal behavior. And we also extended some of this work for capturing text, and can you sort of find correlations both between the text and the ratings. But unfortunately, limited time. I want to take a couple of minutes to talk about scalability, which will touch upon a lot of what Vegeli's mentioned for tensor factorization. These models are huge. They're capturing lots of items and lots of users. How can we actually do this at scale? Matrix factorization, as I mentioned, can capture concepts like topics. We're saying these users are interested in computer science, let's say topics. There's a bunch of work that happened around the beginning of my PhD on distributed matrix factorization. So Gamul et al. Had one paper, DSGD. Ben Recht et al. Had Hogwild for shared memory systems. For hypergraphs, there was a little bit less. Yukong at the time had one paper with Vegeli's using alternating least squares for learning these models. So we want to sort of try to build on that. We looked at, we want to model attribute hypergraphs. This corresponds to coupled matrix tensor factorization that Vegeli's mentioned. We want to distribute it for the purpose of scalability. We want to do it fast and flexible. I'll mostly focus on the first three. So here we consider this case of time as the third dimension. We say von Neumann, like the Washington Post, let's say last February. Maybe there's a group of users who are interested in sort of news-related things around voting season over this date range. And we want to sort of learn this low-rank factorization. So what we can do is we take this dot product, this three-way dot product effectively, is trying to predict, will von Neumann, like the Washington Post, this February, or last February? And we have some observation, and we can do some local update, meaning we can see how that prediction matches with that observation and do some modification using something like SGD or belief propagation to improve the parameters for that user, that item, and that time. Now, if you have another, let's say, example here, so Grace Hopper like the ACM in 1947, then we can do some updates with her and ACM and that time. And the nice part is these are independent. They're both local updates. They're only going to affect their sets of parameters. There's no risk of a collision. But if you have, let's say, this third point, this blue point here, of Turing liked the Queen this past February, they're not independent because they both have to do with this past February. And that's not really going to work for collisions. So what we find is you can do this parallelized by color, right? You split up your data and your parameters jointly. And what we find is we get this, the red updates correspond to the red parameters, and the green data points to the green parameters, and we can write them in parallel, no problem. We can do different configurations. I'm going to skip over, I guess, the attributed part because we're running out of time. One thing I think is interesting here with the rise of deep learning is that a lot of what we focused on generally is the partitioning of the parameters of servers. I think we've underutilized the partitioning of your data simultaneously. And we've relied instead on the parameter server sort of merging these things and hoping for it to be sparse. But if you think carefully, you can often find sort of ways for these things to not collide and have less noise and stability issues. So the same concept, because it's SGD, nicely extends to many other model families. If we know, let's say, what university affiliation and country they're from. This corresponds to a joined matrix. We can do the joint coupled matrix factorization, matrix and tensor factorization, and you get this similar color, a learn by color parallelization trick. When you do this at scale, we find we can scale. This was at the time on Hadoop, which is kind of a wonky thing now when you consider systems we have today. But we had 47 times faster learning in terms of the size of your data, 13 times faster in terms of the number of parameters, and much, much faster in terms of the rank, because SGD just scales better in the rank than ALS at the time. And we did some follow-up work because Hadoop really wasn't designed for this sort of thing. There's often stragglers, and you can use then some nice statistical properties to actually address your systems issues using the sort of flexibility of machine learning. And so you can look up sort of the work flexi fact, which is, I think a while ago, was at least well cited from SDM. And so given I have a couple minutes left, I wanted to sort of talk about, right now I'm working mostly on deep learning things, and I think all of this work has some relationship with deep learning. For example, for the ratings prediction problem, we've looked at more recently using recurrent neural networks to capture temporal evolution, related to the question that was asked to Vigelis about, oh, how do you deal with patterns in time, right? And I think there are certain discrete assumptions about time that are common in tensors, but it can be sort of handled more flexibly by deep learning. On the flip side, lots of deep learning models actually are matrix factorizations with some stuff in the middle. So in the same way you have, let's say, the block in the corner for your tensor factorization, you might have some nonlinearities in the middle, but a softmax is effectively just the same dot product. So there's lots of similarities that I think we can use many of the same tricks that we've been sort of getting benefits from on the factorization side in deep learning, and some advantages in deep learning that can help solve some of the challenges and limitations of discrete modeling. And with that, I'm happy to take any questions.